Hi guys, in this video we're going to be doing a couple of things. So yesterday your worksheet on domain and range had a kind of last section that is functions that look like this. They may say y equals, they may say f of x equals in place of y, or frankly they may just have the function part and not this part, I'm not sure. However, the way that we can find the domain, so on these ones you'll be asked to find the domain, but not necessarily the range. So remember that the domain is the x values. So what we are looking at, if we're looking at a function that's not graphed, just like the equation of the function, is we're looking for the x values that I could plug into the function and have nothing become undefined, or I guess have solutions that are not real numbers and that sort of thing. Okay, so there's going to be two things that you're going to check for. And those things that you're going to check for are the following. So the first one is you're going to check for a square root or a radical symbol. If you have a square root in your function like this one has here, then we're going to have to restrict the domain, because remember, we cannot take the square root of a negative number. When I say restrict the domain, it means I'm going to have to exclude some x values from the domain. Okay, so I can have certain x values, but there are some that I can't. Like in this case, I can't have any negative x values. So I know that x is going to have to be 0 or bigger in order for this to be true, because remember, if I have the square root of a negative number, that's going to be imaginary. So that's not a real number. So those x values would not be in the domain. So on this, we're looking specifically at real numbers and using the real number system. We're not expanding to complex numbers. So if I have a square root, I need to make sure that the x values, or the part under the square root, I should say, is not negative. The part under the root is positive. Okay, so as long as when I plug these x values in, they give me a positive number under the square root, then this is going to be fine. So on this one, I would say that x has to be greater than or equal to 0. Okay, so another way to say that, and this is fine, you can just leave it like that if you'd like, x is greater than or equal to 0. It can be 0 because the square root of 0 is just 0. It can be 1, it can be 2, it can be 2.5, it can be anything bigger than 0 or equal to 0. It just can't be negative. It can't be something smaller than this, because -1 or -2 under here would not give me back a real number. Okay, so I could also say it goes from 0 to infinity. So either one of these is perfectly fine. Okay, so that's the first thing to look for. The second thing to look for is a fraction with x in the denominator. So if you don't have either one of these things, if you don't have a root and you don't have a fraction with x in the denominator, remember that's on the bottom. The denominator is the bottom of the fraction. If you don't have either of those problems, then your domain does not need to be restricted. In other words, you can just use any x value from -infinity to infinity. So the first thing you want to do on these is check for either of these conditions. Is there a square root with an x under it? I should say that this, if it doesn't have an x under the square root, then it's fine. Or if there is no fraction. All right, sorry about that, a few technical difficulties. But again, so you don't want a square root with an x under it. And that second thing was you don't want a fraction with x on the bottom. Because remember, we cannot divide by 0. So if the x value that is in the denominator were to make the denominator equal 0, then we would also have an undefined function at that point. So a fraction with x on the bottom. So hopefully you've written down the first one is a radical with an x underneath. The second one is the fraction with x on the bottom. And the reason for the top one is because we can't have a negative under our square root. The reason for the second one is because I can't divide by 0, or dividing by 0 is undefined. Okay, so as I was saying before, if you don't see either of these problems, or of these, not necessarily problems, but of these conditions, then you will just have a domain that goes from negative infinity to infinity. So let's take a look at some other examples, but let me finish writing this first. So if we have a fraction with x on the bottom, we need to make sure that we exclude our domain because dividing by 0 is undefined. Okay. So basically we have to make sure that our x values don't make the denominator equal 0. So we'll look at a couple of those examples as well. On this one, again, x just has to be greater than or equal to 0. Okay. So let's go ahead and look at the next example. So again, in this one, I have a square root. So I have to think about excluding my domain. Because of the square root, I need to make sure that the value under here ends up being greater than or equal to 0. So the way to do that is to take the expression that's underneath, the x plus 6 in this case, and set it equal to 0, because it is okay if it equals 0, but it just has to be bigger than that. Like whatever value makes this 0, then the only ones we can count have to be bigger than or equal to that number. So just take whatever's underneath, set it equal to 0, solve for x. So x equals negative 6. So when x equals negative 6, if I were to plug an x of negative 6 in here, that's giving me negative 6 plus 6 underneath the radical, which is the square root of 0. The square root of 0 is just 0, so that one's defined. If it's bigger than negative 6, like if I put negative 5 or negative 4 in here, negative 5 plus 6 is a positive 1, negative 4 plus 6 is a positive 2, so anything bigger than negative 6 is going to give me values that are real numbers for y. Okay, so x has to be greater than or equal to negative 6, because if it gets less than negative 6, like if this were a negative 7, for example, then I would get a negative 7 plus 6, which is negative 1 underneath the radical, which would be imaginary. Okay, so we don't want any imaginary y values here. We only want real y values. So as long as x is greater than or equal to negative 6 in this case, then y is going to be 0 or bigger. Okay, so that's what we're trying to do here. So this is the domain of the function. The domain is any x value greater than or equal to negative 6. So let's try another one. So on this one, another radical. So I guess we're doing all the radicals in a row here. Because of the radical, I need to make sure that any x's I put here make this equal to 0 or bigger. So again, I'm going to take what's under the radical and set it equal to 0. I'm going to solve for x. So in this case, I'll add 1 to both sides. So x equals 1. So x equals 1, that just is telling me the value that makes this equal 0. Because it can be 0, it just has to be it just has to be 0 or bigger. So if x is equal to 1, it's going to give me the square root of 0, which is 0, which is fine. If x is bigger than 1, like 2, 2 minus 1 is a positive 2, so that's going to give me a positive number. But if I were to put anything less than 1 in there, like a 0, 0 minus 1 is negative 1, or if I were to put a negative 1 in there, that's going to give me negative numbers underneath the square root. And so I would not want anything less than this. So x is greater than or equal to 1. Again, I could write it in interval notation as 1 to infinity. Okay, so that's my domain here for this function. Okay, so now let's look at some different types of examples. So in this one, notice that I have underneath my radical, I've got this x plus 1. So this one's a fraction with an x in the denominator. So this one I also have to think about restricting the domain. In other words, the domain here can't just be all real numbers for x. It can't go from negative infinity to infinity because there is an x value that will make this denominator equal 0, and that x value is -1. But you can always find it by just taking the denominator and setting it equal to 0, and then solving for x. So you get x equals -1. So if x were equal to -1, then when I plugged it in right here, I would get -1 plus 1 equals 0. And that's exactly what I wanted to find, is the value that made that 0, because if I take 4 divided by 0, that's undefined. If you try it in your calculator, you're going to get an error because you can't divide a number by 0. So because of that, I can plug any x value into this function that I want as long as it's not 0. Okay, so I can write this a couple of different ways. One of the, I guess, things to think about when you're doing this is that -1 is the only x value that won't work. So I could write it as -infinity to -1 and put a round parenthesis there, because that means it's going to include everything right up to -1, but just not include -1 itself. But then I would be leaving out the ones that are bigger than -1. So I would have to do the same thing, -1 to infinity. So this tells me any x value on the number line is fine except for -1, and even a number like right up next to it, like -0.999. Okay, that's going to be fine. -0.999 would be fine. -2 would be fine. -2.5 would be fine. Any value that is on the real number line except for -1. Another way to write that would just be to say that it was all real numbers except for -1. So you would just say all real numbers except -1. But a lot of times we kind of just take that part for granted and we just say x does not equal or cannot equal -1. So this is definitely the easiest way to write it right there, and I'm fine with that. But I just wanted you to see that there are more than one way. There is more than one way. So we basically, again, check for if there's a radical or a square root. If there's a square root, we need to make sure the x values that go in all make it positive. If there's a fraction, we need to make sure that the denominator will not be 0. So that's just usually going to exclude 1 or 2 values, depending on how many x's are on the bottom. Let's go ahead and look at some examples where we wouldn't have to worry about it. So like on this one right here, let's ignore this part right here, the find g of -8. We're just looking at the function. We want to find the domain here. So because I see no square root here, and I see no fraction with the variable in the denominator, I know that the domain here is just going to be -infinity to infinity. Okay, so really just check for those two things. And if they are not there, then you don't need to worry. G of x equals x plus 2. Again, I don't see a square root and I don't see a fraction with x on the bottom. So the domain here is just going to be -infinity to infinity. Okay, let's just do like one more example of this, and then we're going to go on to some other new things that we're learning today. So like on this one, for example, we have 4 over x minus 2. Because x minus 2 is in the denominator, I need to make sure that the x value that makes that equal 0 gets excluded. So, sorry, my marker's being weird. X minus 2 equals 0, add 2 to both sides, and then I would get that x equals positive 2. You guys are pretty used to that by now, so you probably don't really need to write all of this out. But again, remember here, we have to say what x cannot be. If it's just one value, we usually just say it cannot be that value, even though we really mean it can be any value except for that value. So now let's go ahead and take a look at the things that we need to learn today. The section number today, oops, I'm clicking on the wrong thing, is 1.2 Part A. And we are going to be talking about functions that increase or decrease. So if you are looking for an increasing interval, that interval is going to be going uphill on the graph. So increasing, I might want to write this down, intervals go uphill. So we have, when we're doing this, we have to kind of look at our graph. Like if I'm going from left to right here, this is going uphill. But if I'm going from right to left, it would be going downhill, right? So it depends on which direction I'm coming from. So it's always really important to read graphs from left to right. Okay, so we have to definitely have a direction here where we're not going to be able to tell what's increasing or decreasing. So just like you would read a book from left to right, we want to read a graph from left to right, which means I'm going to start over here and go this way, which means this part right here is uphill. So this part right here is an increasing section of the graph. Okay. Increasing intervals go uphill. They can go uphill as a straight line. They can go uphill curving, but they will definitely be going uphill. Okay. Decreasing intervals, you guessed it, they go downhill. And again, we've got to make sure we're reading our graph from left to right. So this section right here is decreasing. And then we have constant sections of our graph, and the constant sections, or constant intervals, they are going to be horizontal lines on our graph. Okay, so this part right here is constant. So constant means it's not going to change. It's not going to go up or down. It's just going to go constantly out. So that's what a constant interval looks like. So the way that we say where it's increasing, okay, is, let's try and change colors here. The way that we, I guess, call out the part that's increasing is by, this thing is covering my colors, is by saying, well, the increasing part here, and we're going to use an interval that comes off the x-axis, so I want to see where it starts increasing, and that's the x value where it starts, so that would be -2. And then I want to look at the place where it stops increasing, and that would be at x equals 0. So this function increases from -2 to 0. Notice I did the square bracket on the filled in circle and the round one on the open circle. At that point, it hops down here and at the x value of 0, and then it starts heading downhill. So this is decreasing from, oh, I forgot my C. It's decreasing from x equals 0. So again, we're looking at our number line is the x-axis. It goes downhill and stops right there. The x value where it stops is 2. So that's the decreasing interval. The constant interval is the one that just goes straight out, starts here and stops here. So that goes from 2 to 3, from x equals 2 to x equals 3. And whoops, I made a mistake. That should be a square bracket on that side. So there's our constant interval. All right, so let's go ahead and look at some other examples quickly. If I can get this thing to advance. Okay. So here we have another one. This one has kind of more rolling hills, but same process. We're going to go from left to right. So this piece right here is increasing. Notice that there's another section here that is increasing. Those are the parts that are going uphill. And then we have a piece here that's decreasing, that's going downhill left to right. Notice there's no constant intervals here. So on constant, I would just say none. Increasing, again, I need to check x values. So on this one, there's an arrow, which means it's going to keep going out that way and down. But for the interval coming off our x-axis, we care about this direction. So it's increasing. Always do left to right. So this arrow is going to go the furthest left. It stops increasing right here at the top of this hill, and that's at x equals 2, negative 2. So it increases from negative infinity to negative 2. It decreases from negative 2 to approximately 0. It might go a little beyond, maybe like 1/4. So we could say decreasing from 0.25, nope, from negative 2 to negative 2 to 0.25. And actually, when we're doing increasing and decreasing, I actually forgot this on the last slide. We don't need to worry about square brackets or round brackets. If you're just talking about increasing or decreasing, you're just going to use round parentheses every time. You don't need to worry about the endpoints on increasing and decreasing. So then at 0.25, it starts increasing again. So I'm going to put this one up here in the increasing intervals. And that continues to increase indefinitely. It's going to go out to positive infinity. Okay. So from negative infinity to negative 2, it's increasing. Between negative 2 and 0.25, it's decreasing. And then from 0.25 to infinity, it's increasing again. So let's look at another one. So this one also has 2 sections that are decreasing, and then the other 2 are increasing. So, and there's no constant. So the increasing intervals are, if I go furthest left, I've got an arrow. It's going up mostly, but that means it's still going this way. So negative infinity to negative 2, nope, to negative 1.5. Because this whole part decreases till it gets to right there, and the x value there is negative 1.5. Okay, then it starts to, oh, sorry, that's decreasing, isn't it? So it's decreasing because from left to right it's going downhill, so there's 2 decreasing intervals. I misspoke. So negative infinity to negative 1.5 is decreasing. Then it starts increasing from negative 1.5 and then ends up here at, looks like 0.5. So negative 1.5 to 0.5 is increasing. Again, remember, you're using the x values. So from 0.5 to 3, it's decreasing. And then from 3 to infinity is increasing, because that side is going to keep going indefinitely. Okay. So let's just try one more example, and then I'll be out of your hair. So this piece right here is increasing till we get to the top here. So this is increasing. This piece is decreasing. So our increasing interval, if I say the x value where it starts and stops, would be right here, which is negative 4. And it increases until it gets to here, which is at x equals negative 2. And then it decreases from that negative 2 till it gets to the end point right here, which is at negative 1. All right, guys, give these a try. If you have questions, please let me know, and I will see you on Monday.